In the world of uh, massive, hyperscale artificial intelligence data centers, a network can look mathematically perfect on paper.
Oh, absolutely. Flawless.
Right, flawlessly engineered, perfectly compliant with every single industry spec, and still, it can still spontaneously tear itself apart the very moment you turn it on.
It really is the ultimate engineering paradox. You build something according to the absolute letter of the law, and the physical universe just refuses to cooperate.
Welcome to the deep dive. Our mission today is to figure out why these ultra high-speed networks, specifically, for you listening, we're talking about the 400G, 800G, and that bleeding edge 1.6 terabit level, why they're suffering from this exact phenomenon.
Yeah, it's a massive issue right now.
It is. And we are pulling our insights today from a really brilliant insider article. It was published by Axiom, and it's titled Inside the Stack: What Breaks First in 400G, 800G, and 1.6T Deployments.
Written by Dr. Carlos Burgo.
Yes, Dr. Berto. He's a PhD with over 25 years of experience building telecommunications and AI infrastructure. So he really knows exactly where the bodies are buried in these massive data centers.
He really does. And to really grasp what Dr. Berto is arguing here, you have to appreciate the sheer, just mind-bending scale of a 1.6 terabit connection.
Right.
At those transmission rates, the standard engineering playbook completely falls apart. I mean, he points out that the standard bill of materials, the BOM, which is the foundational document of literally any hardware build it, totally fails to predict real-world stability.
Totally fails, which is wild. So today we're exploring the invisible forces, signals, heat, power, human hands that secretly destroy these networks. Okay, let's unpack this.
Let's do it.
To understand why an incredibly advanced AI network fails, we first have to talk about the illusion of the perfect plan. According to the source, the BOM encodes what they call nominal compatibility. But wait, isn't a bill of materials literally just a parts list? If part A is designed to fit into part B, shouldn't they just, work together?
Well, in a vacuum, yes. A BOM is essentially just a spreadsheet checking off boxes.
Okay.
It guarantees that the components meet the industry standards individually. It operates on this assumption that if you follow the reference topology, the map, you will have enough margin.
Ah, margin. Margin is a concept that dominates this entire article. For anyone listening to this deep dive who maybe isn't an infrastructure engineer, how should they visualize this?
Think of margin as your operational breathing room. It's the shock absorber built into the system to handle, well, physical errors.
Like a buffer.
Exactly. In older, slower networks, say your standard enterprise server racks, you had an abundance of free margin. If a fiber optic cable was bent slightly, or a connector had a microscopic speck of dust on it.
Which happens all the time.
All the time. The system just had enough built-in tolerance to simply absorb that signal degradation and keep transmitting your data flawlessly.
So plenty of room for error. But Dr. Berto notes that as we push into these 1.6T speeds, we're relying on this incredibly dense 224G class electrical and optical ecosystem.
Right.
And at that level of density, that free margin just shrinks to virtually zero.
It completely vanishes. And this is where the spreadsheet betrays the engineer.
It makes me think of like building a hyper-advanced sports car directly out of a high-end catalog.
Oh, that's a good way to look at it.
Right. You order the world's best engine, the most aerodynamic chassis, the most advanced transmission. Individually, every single component is world-class and perfectly to spec.
Absolutely.
But if you assemble that car without accounting for the actual, chaotic vibration of the road, the specific friction of the asphalt or the wind shear when you hit 200 miles an hour,
the car shakes itself apart the second you leave the garage.
Exactly.
What's fascinating here is how that sports car analogy maps perfectly to the tails of a statistical distribution.
How so?
Well, when manufacturers validate these optical components and these network switches, they test them in pristine, heavily controlled lab conditions.
Oh, sure. White glove treatment.
Exactly. They have perfectly clean interfaces, no physical vibrations, ideal airflow. They are driving your sports car in a vacuum.
But out in the wild, in production data center, you're out on that messy, vibrating road. You're dealing with a distribution of tiny overlapping degradations.
Which the BOM completely ignores. The BOM only tells you that the system works in the dead center of the bell curve.
Right.
But the real-world environment where all the outages actually happen, that lives out in the tails of that distribution.
And the messy edges.
Yeah. And because the free margin at 1.6 terabits is essentially zero, those tiny real-world deviations that used to be, totally harmless, they suddenly become massive service-impacting events.
Because there's literally no shock absorber left. So if the margin's completely gone, what is the very first thing that falls off the tightrope? According to the text, it's the invisible signal itself.
Signal integrity is always the first casualty. Always. To push 1.6 terabits of data, these systems use a modulation scheme called PAM4.
I want to pause you right there, actually, because the article mentions PM4 repeatedly as this major friction point. What is the actual mechanism there? Why is it so much more fragile compared to older networks?
It really comes down to how you encode a 1 and a 0.
Okay.
Legacy systems used simple modulation. Imagine turning a light bulb on for a 1 and completely off for a 0.
Bright or dark? Simple enough.
Very simple. It is very easy for a receiver to tell the difference between bright light and total darkness, even if, say, the lens is a little dirty. That is a high-margin signal.
Makes sense.
But PM4 doesn't do that. PM4 crams more data into the exact same channel by using 4 distinct voltage levels instead of 2.
Wait, 4?
Yeah, so instead of just on or off, you essentially have off, dim, medium, and bright.
Ah, I see the trap. Now, the receiving computer has to differentiate between dim and medium at billions of times per second.
You've got it. The voltage thresholds, what engineers call the eye diagram, they shrink drastically. The system has to be incredibly precise to read the data correctly.
Wow.
So PM4 is mathematically brilliant and it's incredibly efficient, but it burns through your margin incredibly rapidly.
And things are, they're rarely precise in a physical rack because of what the text calls interface count creep.
Oh, yeah. The physical reality of the build.
Right, because the BOM assumes a pristine direct connection from point A to point B. But in a real data center, human beings get involved.
And we make messes.
We do. You need patch panels to route the massive bundles of cables. You throw in a temporary jumper cable because you're waiting on a back-ordered part. And, of course, that temporary cable stays there for 3 years.
Oh, inevitably. And every single one of those architectural additions is a mating cycle. It is 2 pieces of microscopic fiber optic glass meeting each other. And every single physical connection introduces a channel discontinuity.
The source gets highly technical here. It says these discontinuities localize, and that one bad reflection point can, quote, totally dominate the link's impulse response.
Yes.
I mean, I understand a reflection like light bouncing off a dirty glass connection, but what does dominating the impulse response actually mean for the listener who might be, say, troubleshooting one of these racks?
Okay. Think of an impulse response like shouting into a canyon to hear the echo.
Okay, I'm with you.
In a clean canyon, you shout, and the sound travels cleanly to the other side. But if there is a massive boulder right in the middle, your shout bounces off it and creates this harsh, localized echo.
Oh, I see.
In a fiber optic cable, if you have a bad reflection point from a messy patch panel, the light pulse bounces back. That localized echo interferes with the billions of other light pulses trying to get through. It dominates the signal.
So the data just gets completely garbled by its own echo.
Exactly. And this is where the network attempts to save its own life. It heavily relies on an algorithm called FEC forward error correction.
Which the text describes almost like a network-level autocorrect.
That is a great way to think of it. It's a mathematical algorithm that looks at the garbled, echoing data, guesses what the corrupted bits were supposed to be, and fixes them on the fly.
Like when my phone changes my typos.
Yes. In a healthy, older system, FEC is an occasional safety net. You hit a bump, the autocorrect fixes the typo, and you move on.
Right.
But at 1.6T speeds, because of all those tiny reflections and the extreme sensitivity of PM4 we just talked about, the FEC algorithm starts running continuously.
It never stops.
Never. It becomes a permanent crutch, working at maximum computational capacity just to keep the link from collapsing.
I have to ask you about a specific line in the text regarding these signal failures, because it genuinely made me laugh out loud.
Oh, I think I know the one.
Dr. Berto mentions that when engineers see these lane-local error bursts, they start resorting to, quote, fixes that look like superstition. Like, they will literally just reseat a cable, unplug it, and plug it back in, or they'll move it 1 millimeter to an adjacent port, and suddenly the massive multi-million-dollar AI cluster works perfectly again. I mean, come on.
It sounds crazy.
It does. Wait, the text says engineers use fixes that look like superstition, like reseating a cable or moving to a different port. Does unplugging it and plugging it back in actually fix the hardware, Or is it just dumb luck?
It feels like a superstition, absolutely, but it actually makes perfect physical sense based on the physics we just discussed.
Really?
Yeah. When you physically reseat a fiber optic cable, you are shifting how those